Imagine drifting with a gentle hum through a darkness so pure that even the word night feels too bright. There, a golden mirror opens like a slow breath. The James Webb Space Telescope, folded into the quiet at the Sun-Earth L2 point, listens for light that left before galaxies had grand designs. It doesn't chase the bluest flames. It waits for the oldest embers, stretched into infrared whispers by the expanding universe, and it turns those whispers into pictures and spectra that feel like time finally speaking. The core idea is simple and strangely comforting. The universe builds complexity earlier than we thought. When JWST first opened its eyes, it found not just little smudges of early starlight, but surprisingly bright, surprisingly structured galaxies within the first few 100 million years after the Big Bang. Some looked too big, too luminous, or too chemically enriched for their age. News headlines called them impossible. The reality is softer and more interesting. They are not impossible. They are teachers. And when Webb looked inside them, using not only images, but the detailed fingerprints of starlight, it found clues to how the first cities of stars were laid down, street by street, gas by gas, element by element. Here's an early surprising fact. JWST's JADES team confirmed galaxies at redshifts around 12 to 13, meaning the universe was roughly 330 million years old when those photons began their journey. One of them, JADESGST 13-0, sits at Z, approximately equals 13.2, about as far as starlight can reach us without losing its identity entirely. Another, GNZ11, long famous from the Hubble era, has been revisited with Webb and shows startlingly strong ultraviolet emission lines, hinting at very hot, massive stars or even a compact black hole at its center. And the SEERS survey, the Cosmic Evolution Early Release Science Program, reported multiple galaxies beyond redshift 10, some with spectra that leave little doubt. These are not tricks of dusty low redshift imposters. They are bona fide snapshots of cosmic dawn. If you close your eyes and imagine what inside means for a galaxy this young, think of texture. Not smooth swaths of starry fog, but clumps, knots, and filaments. JWST's sharp infrared eyes see compact cores only a few hundred light years across, with star formation rates so high that their stellar masses could double in 100 million years or less. The light is often intensely blue in the ultraviolet, implying very little dust and very young stars. Yet in some cases, Webb detects the fingerprints of oxygen and nitrogen elements that must come from earlier generations of stars already present. How can chemical richness appear so quickly in a universe barely awake? This is the puzzle that drew so much attention. Early analyses suggested that a few galaxies at redshifts 7 to 9 might have stellar masses rivaling today's Milky Way progenitors, only 500 to 700 million years after the Big Bang. That would be difficult to reconcile with our standard model of cosmology, which grows galaxies, hierarchically small structures first, then bigger ones. But when Webb looked closer with spectroscopy and improved modeling, many of those masses came down. Emission lines that brighten infrared bands had been fooling older telescopes into overestimating the stellar mass. Even so, the number of luminous galaxies at Z, greater than 10, still seems higher than expected. Not impossible, but surprising enough to make theorists sharpen their pencils. What exactly did Webb see inside these early galaxies? Bright emission from oxygen, O3, and hydrogen, when those wavelengths are accessible. At higher redshifts, where rest optical lines shift beyond Webb's ionized spectrograph, it catches ultraviolet tracers like C3, O3, and He2. These lines whisper about temperatures, densities, and ionization. Many spectra show equivalent widths of O3 and H above 1,000 angstroms at Z tilde 7 to 8, which is a technical way of saying the star-forming gas is being blasted by unusually intense ultraviolet radiation from very young, massive stars. And in at least one case, at Z tilde 8.7 Sears 1019 JWST, detected the telltale signatures of an actively feeding black hole, only about 570 million years after the beginning. Let your mind move slowly over that image. A tiny galaxy, a few hundred parsecs across, where gas is dense and hot, and stars form in surges. The radiation fields are strong. Supernovae are beginning to stir metals into the mix. Outflows may already be pushing against the dark matter's gravitational pull. It does not feel like a serene spiral. It feels like a glinting workshop. And somewhere in that bright center, a black hole could be accreting, shaping flows, and competing with newborn stars for fuel. There is continuity here with what came before. Hubble and Spitzer had hinted at early galaxies. GNZ11 at redshift 10.6 was one of them. We also saw strong Balmer breaks that suggested mature stars in some objects, though we now know that nebular emission lines can mimic those breaks. Webb didn't just add resolution. It transformed ambiguity into structure. With NIRCam imaging to find candidates and NIRSpec or NIRCam prism spectra to measure redshifts and lines, JWST turned remote spots of light into places with known distances, known gas conditions, and sometimes even known element ratios. And what does that do to the grand story? It softens the old boundaries. Before JWST, many models predicted a steep drop in galaxy numbers beyond redshift 10. Webb found more bright galaxies than expected. The cosmic recipe needs adjusting. Perhaps star formation in the smallest halos is more efficient at the dawn. Perhaps the initial mass function, the way stars are distributed from small to large, tilts slightly toward massive stars when metals are scarce. Perhaps dust builds quickly in some places, but not others, hiding some galaxies while letting others shine. None of these revisions break the universe we know. They refine it. There is an intimate, almost tactile pleasure in following a photon story. Think of a hydrogen atom in a pocket of gas 330 million years after the Big Bang. A massive star begins to shine nearby, flooding the region with ultraviolet light. An electron is pulled away and then finds its way back, stepping down energy levels like rungs. In that step, a photon is born. It leaves the atom at a wavelength, perhaps in the Lyman series, short, sharp, eager. space expands. The photon stretches. Through epochs of mergers and quiet times, through reionization's fog, it grows long enough to be captured by a gold mirror governed by microns. Through cooling lines and the hum of gyros, through mirrors that align to within a fraction of a wavelength, that photon becomes a line on a spectrum. It holds a temperature in its slope, a density in its ratio to another line, a story of starlight hidden in its width. We will take 5 slow steps through this story. We'll revisit the universe that JWST inherited from Hubble. We'll walk inside the gas and stars Webb measured, and into how those measures rewrite our expectations. We'll touch the edge's disks forming earlier than comfort, black holes glowing when they should be merely seeds, galaxies carving bubbles in a neutral intergalactic medium. And we'll let the quiet of the instrument guide us to what all of this means for physics, for models, and for our sense of time's first architectures. For now, breathe with the telescope. The oldest light is not shouting. It is patient. And it is full of detail. To understand why JWST's first galaxies felt so unexpected, it helps to sit for a moment with what came before. Hubble saw far, but it saw mostly invisible and near-infrared bands that left the highest redshifts out of reach. Spitzer filled in the mid-infrared, but with limited resolution and sensitivity. Together, they painted a picture of a universe that got busy quickly. By redshift 6, about 1 billion years after the Big Bang, galaxies were already forming stars vigorously, and reionization, the process that turned the universe from neutral fog to ionized clarity, seemed largely complete. There were highlights. GNZ11, a compact, bright galaxy at Z approximately equals 10.6, stood as a lonely outpost in Hubble's maps. AMA CS1149JD, 1 at Z, approximately equals 9.1, showed a surprising detection of the 0388 micron line with Almy, implying oxygen existed just 500 million years after the beginning. But past redshift 10, the count of galaxies dropped sharply. The theoretical expectation was that dark matter halos, those gravitational wells that gather gas and form stars, were too small and rare at early times to host many bright galaxies. Star formation efficiency should be modest. Feedback from young stars should blow out gas in these tiny systems, regulating growth. Then Webb arrived. Its design choice, to look in infrared with exquisite sensitivity and resolution, was exactly what early galaxies required. Using an IR cam, teams like JWST, Advanced Deep Extragalactic Survey, Sears, Glass, and Uncover mapped deep fields with color filters tuned to catch dropouts. Galaxies whose light vanishes in bluer bands because of the Lyman break, the signature of a universe opaque to wavelengths shorter than 121.6 nanometers in the rest frame. Those candidates were then tested with spectra from UNIR spec or the UNIR cam grism. If the sharp edge of the Lyman break was seen at the right place, the redshift became secure. If emission lines like O3 or C3 appeared, the physics began to speak. 3 unusual discoveries quickly emerged. First, the bright end of the galaxy luminosity function, At Z greater than 10 was richer than anticipated. More luminous galaxies existed early than many models predicted. Second, the star-forming regions inside these galaxies were extreme, with O3 plus H-beta equivalent widths surpassing 1,000 angstroms at Z tilde 7 to 8 signatures of intense, very young starbursts. Third, compactness. Half-light radii often measured only 200 to 500 parsecs. These were tiny by today's standards, but their central densities were high, and their specific star formation rates, how fast they form stars relative to the mass they already have, could be 5 to 20 per billion years, meaning fast growth on cosmic timescales. The early shock headlines, impossibly massive, came from a small subset of photometric candidates at Z tilde 7 to 9 that looked red in Spitzer's bands, a color often interpreted as a Balmer break from older stars. With JWST's spectra and more complete photometry, astronomers realized that bright emission lines had been sneaking into those bands, mimicking a large population of older stars. Many masses dropped by factors of a few. The surprise did not vanish. It refined. Even with revised masses, the number density of bright galaxies remained higher than expected at Z greater than 10. But that is different from existential crisis. It is a clue that early star formation is more efficient, more bursty, or more top-heavy in its stellar distribution than assumed. Now, a gentle pause on the word metallicity. In astronomy, metals mean all elements heavier than hydrogen and helium. The first stars, population 3, were predicted to form from pristine gas, with essentially no metals. Without metals to cool the gas efficiently, simulations suggest those first stars were massive and short-lived, flooding the universe with ultraviolet light, and then seeding the next generation with carbon, oxygen, silicon, and more. JWST, by measuring lines like O3 and C3 in the ultraviolet at very high redshift, and O3, Ni3, and Balmer lines at slightly lower redshift, has begun to sketch metallicities in the earliest galaxies. Many fall around 10% to 50% of the Sun's metallicity by redshift 7 to 8, which is surprisingly mature. Not solar, but not pristine. That rapid enrichment means star formation cycles, birth, death, and mixing happened efficiently and repeatedly. Another underappreciated shift Webb brought us clarity about dust. Hubble's ultraviolet slopes suggested very blue colors little dust in many early galaxies. JWST largely confirms this at Z greater than 10. UV slopes, often described by the parameter beta, are typically around 2.3 to 2.7, consistent with youthful, low-dust systems. But by Z tilde 7 to 8, some galaxies show evidence of dust attenuation, and ALNA has detected dust continuum in several high-redshift systems. Dust forms in supernova and in the envelopes of dying stars, and its presence so early hints that cycles of starbirth and star death were quick. It also means some stars are hiding. If dust absorbs their light, some of the early mass growth could be harder to count without careful accounting. And here is a quieter revelation that Webb's wide field of view and depth enabled: early morphology. Some galaxies at Z tilde 6 to 8 show hints of disks' elongated shapes with light profiles that resemble rotation-supported systems. We do not have many resolved rotation curves at these redshifts yet, but ANIR-SPEC's integral field unit has already caught rotating gas at slightly later times, and the growing evidence suggests ordered structures appear fast. In a universe often described as chaotic in its youth, there are pockets of early order. Consider G and Z11 again, not only as a distance marker, but as a physical system. Recent JWST observations detected strong ultraviolet lines, like N4 and C3, with ratios that hint at either very hot, metal-poor stars or a compact active nucleus. There is tentative evidence of nitrogen enrichment that would require earlier generations of stars to have lived, died, and returned processed material to the gas. The galaxy is tiny and intensely star-forming. It is a reminder that inside an early galaxy, processes unfold at speed. Enrichment, ionization, potential black hole growth, and outflows all stacked into a compact region. One more thread: galaxies and their surroundings. During reionization, the intergalactic medium was patchy, some regions ionized, others still neutral. Surveys that align JWST galaxies with absorption seen in the spectra of background quasars, such as IGER and related programs, are finding that bright O3 emitters tend to sit near transparent windows in the Lyman alpha forest. In plain terms, early galaxies seem to carve ionized bubbles around themselves, and those bubbles can be tens of thousands of light years across. Inside a young galaxy, then, is not only stars and gas, it is a growing sphere of influence on the cosmic fog. Let the scene linger. Webb, built to be cold, watches without rush. The data come in as counts and wavelengths, but when arranged carefully, they reveal beginnings that are both smaller and more intense than many had expected. This is the ground on which we'll now slow down further and step into the spectroscopy, the actual lines that describe the temperature, density, and age of the first star factories. When astronomers speak about what's inside a distant galaxy, they often mean something very specific. The physical state of the gas, the mix of stars, and signs of compact engines like black holes. JWST's great gift is that it records this information as spectra arrayed with teeth. Each tooth is an emission line, and its height, width, and spacing carry meaning. Take a galaxy at redshift 7. At that distance, rest optical lines like O3, 5,007 angstroms, and H, around 4,861 angstroms, are shifted into JWST's near-infrared, where NIR-SPEC can split them by wavelength. Many of the earliest NIR-SPEC spectra showed O3 plus H equivalent widths above 1,000 angstroms. That is a remarkable value. In the nearby universe, values so high are rare. It indicates that the galaxy's light is dominated by nebular emission reprocessed from intense young stars, not by older stellar continua. From line ratios like O3H and Ni3O2, one can infer the ionization parameter, essentially how many high-energy photons are available per hydrogen atom, and it is high. electron temperatures around 12,000 to 20,000 K, and densities from a few hundred to several thousand particles per cubic centimeter are common in these compact regions. Now, push to redshifts 10 to 13. At those distances, the rest optical lines slide beyond IR spec's reach. We live instead in the rest ultraviolet. The tools shift to C3, 1907, 1909, 03, 1661, 1666, He2 1640, and sometimes N4, 1486. These lines are weaker and more delicate, but in several galaxies G and Z, one among them, they are clear. The doublet ratio in C3 can diagnose electron density. The presence of He2 at strong levels hints at very hot radiation fields, potentially from massive metal-poor stars or from accretion onto a black hole. Measuring these lines at such high redshift is challenging, but Webb's sensitivity makes it routine where Hubble struggled. One of the quiet revolutions tied to these measurements is the calibration of Xi_ion, the ionizing photon production efficiency. How many Lyman continuum photons, the ones that can ionize hydrogen, a galaxy produces per unit ultraviolet luminosity? Early JWST data suggests Xi_ion values of log 10 around 25.5 to 25.8 in many Z tilde 7 to 8 galaxies, higher than typical lower redshift systems. That matters. Reionization, the clearing of the cosmic fog, needs a budget of ionizing photons. If galaxies at high redshift are more efficient ionizers than expected, they could drive reionization more easily, especially if some fraction of those photons escape their immediate neighborhoods. Spectroscopy also offers ages, not as a date stamped on a calendar, but as a distribution. How long since the dominant stars formed? Young ages tens of millions of years are common in the line-dominated galaxies, but some show hints of older populations. More modest equivalent widths, redder colors once dust and lines are accounted for, and in a few cases, possible Balmer absorption features. JWST has confirmed that not all early galaxies are newborn at the moment we see them. Some have already cycled through bursts of star formation, even by redshift 7 to 8. The impression is of multiplicity, a cosmic classroom with students at different speeds, some sprinting, some catching their breath. Now, black holes. Sears 1019 is one of the earliest unambiguous active galactic nuclei discovered by JWST. At Z approximately equals 8.68, its spectrum shows narrow emission lines and subtle features that, when modeled, require a black hole of roughly 10 million solar masses, accreting matter in a galaxy still actively forming stars. That means seeds, perhaps from the collapse of very massive primordial stars, or from dense star clusters, or from direct collapse of gas, grew quickly. The balance of ideas is still gentle and shifting, but Webb's detection puts a stake. Black hole growth starts early and can coexist with furious star formation in compact volumes. There are also whispers of structure within structure. In lensed fields, where gravity from a massive foreground cluster magnifies background galaxies, JWST resolves star-forming clumps only tens of light-years across. In one notable system nicknamed the Sparkler, Webb resolved dozens of compact sources around a galaxy, some likely globular clusters in formation, or ancient clusters lit up by new stars. While the Sparkler sits at a later time, Z-1.4, similar lensed systems at higher redshift show that star formation in young galaxies often happens in discrete, bright knots. In a few early galaxies, we see off-center concentrations, double cores, and hints of merging. Inside the first cities of stars, neighborhoods were crowded. Add to this the roles of outflows and inflows. JWST's line shapes and velocity offsets measured by comparing, for instance, the position of nebular lines to interstellar absorption suggests that gas is moving. Blue shifted absorption hints at material driven outward by stellar winds and supernova at a few hundred kilometers per second. These winds carry metals into the halo and perhaps beyond, enriching the circumgalactic medium. They also regulate star formation by heating and diluting the available gas. On the other hand, cold streams from the cosmic web likely supply fresh fuel. Though we cannot yet map those inflows directly at Z greater than 7, simulations and indirect evidence support a picture of balance. Feed the fire, vent the heat. If you listen closely to the spectra, you can even hear whispers of nitrogen. In G on Z11 and a handful of others, the detection of nitrogen lines implies that intermediate mass stars, those that produce nitrogen in their late stages, have already lived and died. That timescale is tens to hundreds of millions of years, suggesting earlier generations existed even before the moment we now observe. The universe wastes no time. All these pieces of ionization, metallicity, dust, density, outflows, black holes feed back into models. Simulations like Thesan, Renaissance, Fire, and blue tides have been updated to match JWST's counts and properties. Some adopt star formation efficiencies that rise more steeply at low metallicity. Some allow for burstier feedback cycles that produce the observed high equivalent widths. Some explore mildly top-heavy stellar initial mass functions in pristine gas. None of these are final answers. They are coordinated guesses, tested against the new details Webb offers. The emerging picture is less of a contradiction and more of an acceleration. The same physics, operating in tighter spaces, with fewer cooling pathways and stronger radiation fields, yields a phase of galactic adolescence that glows especially bright. There is an emotional thread here that is hard to resist. These galaxies are ancient in the sense of when they emitted their light, but everything happening inside them is very young. The stars are newborn. The black holes are seeds with ambitions. The gas is hot with first chemistry. And yet, in the quiet between lines on a spectrum, we recognize familiar processes. Gravity gathering, radiation pushing, element cycling. The universe is trying out its first cities, and they already have streets. We will take this understanding outward next, widening from interiors to implications. What early disks mean for structure. How ionized bubbles cohere into a transparent cosmos. And why counts that lean bright nudge us to rethink how quickly the universe learns to build. Step back now, as if standing on a balcony that overlooks the first billion years. The view is still intimate. There is no need to rush, but the scale widens. The galaxies JWST unveiled are not merely curiosities. They are architects of large-scale change. Their light heats and reionizes the intergalactic medium. Their winds decorate space with metals. Their black holes stir gas in their neighborhoods, maybe even regulating how subsequent generations of stars assemble. Consider reionization as a landscape of growing clearings. In the earliest phases, the universe is mostly neutral, meaning hydrogen atoms can absorb ultraviolet photons that would otherwise travel freely. A luminous young galaxy turns on. Its ionizing photons begin to carve a bubble, a region of ionized hydrogen around it. As the galaxy continues to form stars efficiently, if JWST's Xi_ion measurements are a guide, the bubble grows. Nearby galaxies ignite in turn. Eventually, the bubbles overlap and transparency percolates through the cosmic web. Observationally, programs connecting JWST galaxy positions to quasar sightlines have found that bright O3 emitters at Z⁻⁶ tend to sit near spikes of transmitted Lyman alpha flux in the quasar spectra. That is, near islands of transparency. From inside to outside, the influence of early galaxies is measurable. Sizes matter in this growth. The median half-light radii 200 to 500 parsec support the idea that early star formation is not diluted across sprawling disks, but concentrated. Concentration fuels high surface brightness and potent ionization. At the same time, JWST's imaging reveals that some galaxies show elongated, disk-like shapes even by Z⁻⁶. This balanced, compact, yet ordered, suggests rapid settling. Gas loses angular momentum, cools, and forms a rotating structure quickly in at least some halos. Simulations that include realistic feedback have long predicted that disks can form early if the inflows are coherent and the mass assembly not too violent. Webb provides the first widespread hints that nature indeed takes that route in a subset of cases. Now to the brighter than expected number counts at Z greater than 10. In plain terms, there are more luminous galaxies early on than many models projected. What does this imply? One option is a higher star formation efficiency in small halos. Perhaps low metallicity gas can cool via molecular hydrogen and fine structure lines more effectively than thought, forming dense clumps that convert gas to stars with little delay. Another is a stellar initial mass function that skews slightly toward massive stars at very low metallicities, boosting ultraviolet output and line strengths without requiring enormous stellar mass. A third is duty cycle. If star formation is highly bursty, catch a galaxy in an upward burst, and it will look unusually bright. Catch it between bursts, and it fades from view. JWST's maps, which inevitably sample some phases more than others, might be seeing many galaxies in their luminous episodes. There is also the quiet possibility of selection. When the universe is young, everything is small. A few rare regions will have higher than average density. gravity there runs ahead of schedule. If your deep field happens to land on one of these overdensity's cosmic meridians, your counts rise. JWST's multiple surveys help average over this variance, but the hint of patchiness remains. As the catalog of deep fields grows, statistics will settle. For now, the message is cautious and consistent. The early universe is not empty. It is busier than expected. Another surprising detail Webb brought into focus is the chemical quickness of early enrichment. Nitrogen lines at Z greater than 10, oxygen at Z tilde 9, dust by Z approximately 7. These elements teach directly. Massive stars live quickly and die as supernovae, enriching their environment with oxygen and neon within tens of millions of years. Intermediate mass stars take longer to return nitrogen and carbon, but JWST's detections imply that longer can still happen before the universe hits 500 million years old, at least in privileged pockets. Some ALA detections of fine structure lines, like O3 88 microns and C2 158 microns, map cool gas and dust in galaxies at Z tilde 7 to 9 and show kinematic structure, not yet rotation curves, at Z greater than 10, but the beginning of a dynamic story. Black holes continue this theme of acceleration. Sears 1019's black hole around 10 million solar masses at Z approximately equals 8.7 does not break theory, but it tightens constraints. Seed formation must occur promptly, and growth must be sustained. If some seeds form by the direct collapse of pristine, metal-poor gas clouds of 105 solar masses or more, then rapid growth becomes plausible. Alternatively, if the seeds are smaller from massive stars, they need near-continuous feeding. JWST's sensitivity to narrow-line AGN at early times will expand this census, and with it, our understanding of coevolution. The interplay between stellar feedback and black hole feedback in small, dense systems. Let's connect interior details to human-scale analogies. Picture a city that is both ancient in origin and under construction every day. Roads are narrow, but well-defined. New districts appear overnight, springing from warehouses of raw material along the river. The central square houses a furnace that occasionally roars loud enough to quiet the surrounding streets. Every so often, a convoy of trucks leaves the city, carrying materials to neighboring towns, seeding their growth. That furnace is the black hole. The convoys are outflows. The new districts are the clumpy star-forming regions. The old brickwork still warm from last night's kilns is the dust and metals piling up faster than tradition suggested. Two more calm surprises. First, line-of-sight outflows in some early galaxies reach a few hundred kilometers per second, fast enough to carry metals into the circumgalactic medium, but still gravitationally bound to the halo. This recycling reservoir can cool and fall back, setting up oscillations in star formation that may help explain the burstiness detected in equivalent widths. Second, there are early hints that the escape fraction of ionizing photons, the fraction that leak out of galaxies into the intergalactic medium, could be moderately high in some objects. Direct Lyman continuum detection is impossible at these redshifts, but proxies like line ratios, compact morphologies, and anti-correlations between low ionization absorption and nebular emission point to porous interstellar media. If true, then a relatively modest number of bright galaxies could have a large effect on reionization's timeline. All of this loops back to theory, gently but firmly. A standard cosmological framework called dark matter with a cosmological constant remains steady. The growth of structure from quantum fluctuations to galaxy clusters is a story with many checks. JWST's revelations do not overturn this foundation. They enrich the astrophysics that plays within it. Star formation recipes and simulations are being updated. Feedback couplings are being tuned. Chemical yields at very low metallicities are being revisited. Some groups test mild departures, like variations in the power spectrum on small scales, but the mainstream path is to adjust the baryonic physics, the behavior of normal matter, to match Webb's inventories. The cosmic scene is becoming coherent. Small, intense galaxies at early times, a noticeable number of bright outliers, compact disks appearing earlier than comfort, active black holes growing in step, and ionized bubbles expanding around starbursts. All of it held together by gravity's slow hand and light's patient travel. In the final step, we'll return to the human scale, to what it means to live in a universe that learned to build so quickly, and how listening to faint infrared whispers changes our sense of origin. It's calming to remember that the universe has time. A photon from a redshift 13 galaxy traveled more than 13 billion years to reach a sensor, cooled by a cascade of cryogens, in a telescope that needed humans speaking dozens of languages of engineering and patience to assemble. That photon carried a tiny truth. A gas cloud once was hot and dense and bright. And now, in the late warmth of our planet, that truth is measurable. The act of listening changes nothing about what happened long ago. But it changes us. What has JWST taught us, softly but profoundly, about those first galaxies that should not exist? First, that they do exist more of them, and brighter than most predictions offered, and their interiors are as intense as their counts suggest. They are compact, with star-forming regions pressing gas into dense clumps that shine through strong emission lines. Their radiation fields are harsh in a way that only very young stars, and sometimes small active nuclei, can sustain. Their metals and dust appear quickly, evidence of short life cycles that return enrichment to the gas with little delay. Second, the surprises are invitations to refine, not reasons to abandon our framework. The standard cosmological model stands. Where revisions are needed, they are in the details of how stars ignite in metal-poor gas, how feedback alternately drives and throttles growth, how black holes plant themselves and keep up, and how gas accretes from the cosmic web. JWST's spectra give us the numbers we need to adjust those recipes. Ionization parameters, electron densities, equivalent widths, and scaling relations for sizes and luminosities. Each measurement cuts possibilities down to the ones that fit both the data and the physics. Third, those interiors have outward consequences. Elevated ionizing photon production efficiencies imply that galaxies were potent engines of reionization. Outflows seen in line profiles suggest that early enrichment reached beyond galaxies into their halos. Early hints of disks imply rapid relaxation and organization in a universe still crowded with mergers. Reminder that order and chaos coexist, even at the beginning. There is a human echo in this. Galaxies learn to build fast. So do we, when curiosity is fed. The first times we saw deep fields with Hubble, we thought the drop-off past redshift 10 meant a quiet dawn. JWST turned the lights up and showed a busier scene. The feeling is not embarrassment, it is gratitude. The method worked. Predict, observe, adjust, repeat. The texture grows finer. And as the texture grows, so does the sense that our place in the story is neither central nor trivial. We are latecomers with the privilege of hindsight, piecing together how cities of stars rose before there were heavy elements enough to seed planets like ours. Perhaps the most intimate connection comes from time's asymmetry. Those early galaxies are ancient to us, but their light contains youth. They are forever young in our eyes. Their clumpy starbursts, their hot gas, their first metals, they happen now, each time JWST takes a spectrum. In a quiet way, that collapses distance. It suggests that beginnings are not moments lost. They are ongoing, recoverable, present in the data we can still collect. To fall asleep to this thought is to rest in continuity. The physics that shape those tiny galaxies shapes the clouds that lower rain on our cities, the fusion in our sun, the chemistry in the cells that repair themselves as we dream. What comes next is as gentle as it is vast. JWST will keep integrating light from wider fields and deeper exposures. More spectra will refine the mass function at Z, greater than 10, and pin down metallicities and densities with higher precision. Miri and Alma together will chart dust and cool gas in even earlier systems. Surveys that link galaxy positions to the structure of the intergalactic medium will map reinization's topology, not as an abstract trend, but as bubbles and filaments with measurable sizes. Over time, rotation curves will be measured from more early disks, and the census of the first active nuclei will grow. Theories will fold these facts in, and expectations will converge on a picture that feels inevitable only in hindsight. For tonight, it is enough to hold a few images steady. A mirror unfolded in the dark. A tiny galaxy glowing in oxygen and hydrogen lines, its center packed so tight that wind and light push each other into balance. A black hole, still small, sipping. A ribbon of transparent intergalactic medium, carved by photons that escape through porous gas. And us, far away and much later, learning to listen carefully enough that the noise falls and the meaning remains. If you'd like to keep drifting through the universe this way, with stories made of spectra and silence, with facts that invite wonder rather than urgency, consider subscribing. There is so much more to hear